Hey guys. All right, new chapter, chapter 9. So you might think, well, I thought we were in chapter 6 last. Yes, we were. We had to skip a little bit. Sorry. We got to get to energy. So, and it's not like I don't normally do that. So, we're not like missing anything that any other, engineering physics 1 has done. So don't worry about that. All right, so we are in chapter 9, and this is all about energy, okay? And this is where we end, basically. We end in energy, and then in physics 2, we pick up kind of with energy in mind. So, a whole summer of time, and then we have to think about what we learned in engineering physics 1. Sorry, that's just how it goes. And then we will get into things like torque and how it's related to energy and motion. And then that gets us into waves and electricity and magnetism. And that's the basics of our physics class. Okay, so not engineering, sorry, energy. Moving objects. So we've been talking about movement and like speed, acceleration. We've talked about force. All of that takes energy. So energy is the ability to make things happen, and it's associated with heat and electricity. So we don't do a lot of thermal in physics because I don't have a lot of time to do the thermal. I know if you've taken chemistry that you've talked about things like specific heat, and you've probably talked about how to calculate heat with, the mass times the specific heat of an object multiplied by the change of temperature. And all of that is actually calculated into calories. So heat is calculated into calories but can be converted into joules, which is what energy is going to be measured in, which you will figure out. And it's also related to electricity. We've talked about conservation of mass. Now we're going to talk about conservation of energy, just basically saying that there's just a certain amount of energy and it's just transferred from one form to another. It's not created, it's not destroyed, it's just here, and it's just moving from one thing to another constantly. We're getting these, energy, like plants are getting energy from the sun, animals and or us are eating the plants, we eat animals. It's just the circle of life, essentially. And then, that is something that engineers have to do, is they have to harness energy, different sources. So, definitely something that you guys might be involved in. All right, so the first type of kinetic or of energy that we talk about is kinetic energy. Okay, and this is energy due to motion, so that's kind of what you need to remember whenever you're thinking about kinetic, is it's energy that involves something that's actually moving. All moving objects have some kind of kinetic energy. It might not be as much depending on where it is, but it still has it. The more massive an object or the faster it has, the larger its kinetic energy. Then there's going to be potential energy that we'll talk about. So potential energy is actually energy that's associated with its position. So if you think about this roller coaster right here at the very top, when you're at the very top of a roller coaster, you're not moving, but you're getting ready to. That means that you have some potential energy. And the higher you are, the more potential energy you have. So it depends on, in this particular case, since you're at a certain height, that is known as gravitational potential energy. We'll get into different type of potential energy soon. There's thermal energy. So thermal energy is whenever you have you have both kinetic and potential energy. So the sum of those two energies, that's going to equal your thermal energy, how much thermal energy is created for all of that. And then an object has more thermal energy when it's hot than when it's cold. Okay, so if you look at the system of the environment of energy, you've got sort of this image over here that's showing you that it can go in all sorts of ways. So you've got the kinetic going into potential energy. You can go from potential energy to kinetic. You can go from, you can get over into chemical energy. So in chemistry, hopefully you guys got to do some kind of chemical reaction and experiment where you got to see or feel, heat because of mixing certain chemicals together. And that can create, that's energy. So definitely part of the system. When it says the system can be the universe, the system could be the world, the system could be, your chemistry lab. So it just depends on what you're considering to be the system in that case. And I want you to recognize a couple of these other terms. So as long as the system is not interacting with the environment, the total energy of the system is unchanged. So basically, as long as it's inside this box, conservation of energy should be perfectly maintained. And, if you had good enough equipment, you should be able to prove that. Then there's this process that transfers energy from, one form to another, and that's known as work. And it should make sense to call it that because in order to go from potential to kinetic or kinetic to potential or thermal to kinetic, whatever order you want to go in, it's going to take some work to do that. So even if the work is you putting in the effort to do it, it's taking work to do it. And then a process that transfers the energy to or from a system, that's by thermal means, that's known as heat. Okay, and sometimes in chemistry, you probably have seen that heat is denoted with the symbol Q. If you haven't had chemistry yet, don't worry. That's not really important, for me. But you will see how, chemistry in this particular section really are, you're gonna see how they overlap in a lot of situations. So you've got a transfer of energy. This is just an example where it's saying that if you do some work, then you can transfer it to kinetic energy. So the athlete does work by pushing that shot to give it kinetic energy. So that takes some work. Pulling a slingshot. So this is the symbol, this U right here is the symbol for potential energy. And the potential energy that we talked about a few slides ago, I referred to gravitational. This right here, this picture is showing a slingshot. So, if you were to do a slingshot, you've got sort of like a rubber band type situation. If you pull on that rubber band, then that's going to cause you to have potential energy too. It's just not gravitational, it's elastic potential energy, which is just a different type of potential energy. Sorry, I don't know why that door keeps making a sound. Okay, and then here's another example. You've got energy transformation. So now you're going from potential energy to kinetic energy. So like this diver is jumping off, it looks like the side of a cliff. And, so they're at the top of a cliff, which, anything that's at a certain height, could have a potential to fall. And then the diver is speeding up as gravitational potential energy is transformed into kinetic energy. Now we've got energy transformation from a meteor. So now you've got, kinetic energy, that's being transferred to thermal energy. This meteor is moving, and because it's moving, it's creating quite a bit of heat. Okay, so this is giving us the energy principles, so the transformations of energy within a system. So we talked about that picture before, how they can transform from one form to another, which requires work. So the change of the energy in the system is equal to the external work. Okay, so how much work is put in is equal or equivalent to the energy. So whenever you see the word work, you should also think of the word energy, because they're both going to be measured in the same units. They're both in joules. Okay? So that is giving you just a rundown of the basic energy model again, and how all of that can be conserved. All right, so our first quick check. This is saying that a skier is gliding down a slope, and they're going at a constant speed. And it says what energy transformation is taking place. So this one's a little bit confusing because, and I could totally understand where this would be confusing, because a lot of times people are wanting to answer it this way. The book actually answers it this way. So you might have not even have thought to do it that way. You might have thought to even have done it this way. Either way, this basically means the other two, because if you think about the skier starting at the top of that slope, and then, so if they're at the top, then they've got potential energy, and if they start to ski down, then they've got kinetic energy, and if you add both of those up, the total energy is the thermal energy. So that's why it's answer D. All right, so work and kinetic energy for a single particle. All right, so you've got, it's saying to consider one particle that's acted on by one constant force. Okay, so whenever you are moving an object, or even yourself, you're having to apply some sort of force. And if you apply some sort of force times a certain distance, then you're going to end up having what is work. Okay, so that's what it's saying here. If you apply a force, which is a push or a pull on an object. I'm having trouble hearing you. My watch just went off on me. So if you apply a certain force, which is a push or a pull on an object, a certain distance, then you have then created work. Okay? And the figure here is showing that you are going, you're applying a certain force, and this is showing your initial velocity, showing your final velocity, and the change of distance right here. Okay, so this is giving you a before and after situation. And so why did we involve velocity? Well, the first equation that we're actually going to talk about is kinetic energy. Well, kinetic energy is the energy of motion. So if you have any kind of motion involved, then you're going to have to include the velocity. And velocity is actually more important. It is squared, actually, in this equation. And so the equation for kinetic energy is 1/2 times the mass times velocity squared. And this is saying that the kinetic energy depends on the particle's mass and the speed, but not on its position. So where we were discussing in this slide before, this is showing you a change of distance, but if you go to the kinetic energy, it really doesn't matter what the position was. Okay? So you need to know too that the SI unit is joules. So a joule is equal to 1 kilogram times meter squared per second squared. So I just want to point out that this is kilograms. So if it gives you something in grams, you need to make sure to convert that. This is in meters. So again, if it gives you something in centimeters, you need to always just keep those things in the back of your mind, because you know those quizzes and tests are going to give you things that are trying to figure out ways that you've done it wrong. So just kind of always have that you know, sort of in the back of your head. All right, so let's see. This says that ball A has half the mass and 8 times the kinetic energy of ball B. What is the speed ratio of velocity A to velocity B? All right, so if I'm just going to plug in some stuff here for a minute. Okay, so we know that this equation, all right, and could we actually solve for velocity? Absolutely. This is just giving, these are ones that you kind of have to sort of just plug in some numbers. You know, we've done those before. So if we solved for velocity here, you got to move the 1/2 over. So 2 times kinetic energy divided by mass. And if you're getting velocity by itself, you got to do the square root. Okay. So it says that ball A has half the mass and 8 times the kinetic energy as ball B. Okay, so let's do velocity B first. It doesn't matter. I don't know why. We don't have to do velocity B first, but I'm going to, I guess. So velocity is the square root of 2 times the kinetic energy. Well, let's think about that. Ball A has half the mass and 8 times the kinetic energy. So let's just say 1 for the kinetic energy. And then for the mass, let's just say 1. So we basically have just for simplicity's sake, I guess let's do 2 here, so that we end up with the square root of 4, which ends up giving us just an even 2. Okay? Then if we do velocity of A, then let's do that it's 8 times that. So what would that be? 16 divided by half the mass, so 0.5. That's going to end up giving you 8. All right. So now it wants the ratio of A divided by B. So 8/2 equals 4. So B. So that's just one of those fun ones that you end up having to kind of come up with some of your own numbers for, you know. All right, I'm going to stop the video here and start up on